of the partial fraction decomposition integration method. So we know that we're going to be integrating rational functions, which look like p to the x divided by q to the x. And we know that when the degree of the numerator is bigger than the degree of the denominator, we can divide and get a polynomial plus some remainder divided by the divisor. Now, we know that the degree of the numerator, which is the remainder right here, is going to be less than the degree of the divisor, q of x. And we are going to be performing our partial fraction decomposition upon this, this piece right here, okay? So step 2 of the partial fraction decomposition after you've divided is you want to be able to factor your denominator q of x into irreducible linear and quadratic factors. Okay. So we can finally get to our big theorem. And the way our big theorem works is we're basically going to be decomposing the rational function into one of 4 cases. So these 4 cases, they each depend upon how that denominator q of x is factored. So let's take a look. So the first case is you have distinct linear factors. Let's take a look at a representative example. So suppose that you have something like your numerator would be r of x, but your denominator is distinct linear factors. So like x plus 1, and we did another linear factor that's different, like 2x minus 1, and then let's say that you have another one like x plus 3. And what the partial fraction decomposition says is this part, this entire rational function here can be broken up into 3 smaller pieces. Each linear factor is going to be its own function, its own denominator. So you have x plus 1, you're going to have a 2x minus 1, and then you're going to have a x plus 3. And then the numerators are each going to be constants. So these constants might be the same, they might be different. We don't really know what these constants are. And we need to find A, B, and C. We need to find each of those things there. All right, that's case 1. What is case 2? Case 2 is kind of similar to case 1. We have repeated linear factors. Okay. So in this particular situation, you might have, your remainder r of x up top there, and then your denominator might be something like x plus 1 cubed. So when you look at this guy, the denominator only has linear factors, but the linear factors aren't distinct. They're not different like they were in case 1. In this particular case, the linear factor x plus 1 was repeated 3 times. So how does this decompose? Well, in this case, we're still going to have 3 separate fractions, but take a look at how each of these fractions look. So the first denominator is just going to be x plus 1. For the second denominator, it's going to be x plus 1 squared. So because it's repeated, the x plus 1 has to repeat as a factor once, twice, and 3 times, like this. Okay. Now you ask, what about the numerators of each of these 3 fractions? Well, the numerators could be different. So we're just going to put a, b, and c here. And again, we need to solve for what a, b, and c are. Okay. Let's take a look at the third case. The third case is going to be what we call distinct, irreducible quadratic factors. So remember, we really need our quadratic factors to be irreducible, because if they can be factored further, they might turn out to be like case 1 or case 2. As an example, let's look at r of x divided by x squared plus 1 and x squared plus 2x plus 2. So when we look at these denominators over here, this is an irreducible quadratic, and this one is also an irreducible quadratic. And we could check that by using the discriminant. How is this going to decompose? Well, because we have 2 distinct factors, we're going to have 2 fractions. So this rational function is going to decompose into 2 fractions. The denominator of the first one is going to be x squared plus 1. And the denominator of the second one is going to be x squared plus 2x plus 2, like that. What about the numerators? In this case, case 3, and really case 4, because our denominators are irreducible quadratic factors, the numerators are actually going to be linear, guys. So we're going to have something like ax plus b, and we're going to have something like cx plus d. And in case it's not obvious, we're going to need to solve for a, b, c, and d. Okay. The last case that we're going to have is repeated irreducible quadratic factors. And how is this going to look? Well, let's take a look at an example together. Let's say we have something like the numerator r of x, and the denominator is going to be something like x squared plus 1 to the 3rd power. So in this case, we have a repeated quadratic factor, and it's repeated 3 times, where the power there is 3 times. So we're going to have 3 fractions. The denominator of the first fraction is just going to be x squared plus 1. The denominator of the second fraction is going to be x squared plus 1 squared. So because it's repeated, each power needs to appear. So we're going to have x squared plus 1 cubed for the 3rd fraction. Okay. And then the numerators for each of these will be something like ax plus b, so they're all going to be linear. The second one will be cx plus d, and the third one will be ex plus f. So you're going to need to be able to solve for what those a, b, c, d, e, and f are going to be. And we'll look at examples in class together to learn how to do this. I just want to end things off by mentioning that these 4 cases may be combined. Okay, so what do I mean by that? You know, if my function looks like r of x divided by x plus 1 times x squared plus 1 squared. This is a combination of case 1 due to the distinct linear factor and case 4 because we have a repeated irreducible quadratic. All right. So the numerator for the case 1 part will just be a constant, so we just put an a there. The numerator for the irreducible quadratic part would be a bx plus c. And remember that for the second part, you have to repeat the irreducible quadratic. So the numerator there is going to be dx plus e. All right, so this covers the 4 cases of the partial fraction decomposition. We will do examples in class where I show you how to find the coefficients a, b, c, d, etc. All right, everyone, take care.